Suppose this is the Earth, and my little yellow ball is somewhere very high up in outer space. Let's say it is at a distance of about 100,000 kilometers from the center of the Earth. Now, and suppose from this distance that I drop my ball. Maybe I'm in a spaceship. I drop my ball, and the ball, under the weak attraction from the Earth, since it's so far away, the ball slowly falls, and then it goes faster and faster and faster until it hits the Earth and make a big hole, a big crater. Now, but just before it hits the Earth, what is the velocity? What is the velocity just before it hits the Earth? So this is the exercise that I want to do now. Okay. I need some numbers. I need to know the mass. I need to know the mass of this ball. Let's say 0.2 kilogram. And I need to know, but just before it hits the Earth, I need to know its distance from the center of the Earth, and that would be just the radius. So the radius of the Earth, I shall take it as 638 kilometers. But that's the radius, and that more or less defines the problem. In order to do this question, I can do it using potential energy and energy conservation. Now, we know the formula for gravitational potential energy. That is, potential energy is equal to G m mass of Earth, mass of ball, divided by R with a minus sign. That's the potential energy of the ball. Now I cannot use, I also have the other formula, mgh, but I cannot use this here because this is only valid when the motion of the ball is quite close to the surface of the Earth, where g is roughly constant. But when I take it so far out into outer space, the g decreases a lot. So and as it falls, the g would keep increasing, will increase a lot. So this formula is not valid. I have to use this formula. Okay, using this formula then, the idea is this. At this position, I can calculate a certain potential energy using this formula. When it falls to the surface of the Earth, I can calculate another potential energy using this formula. And from the two answers, I can then find the decrease in the potential energy. And then we say that because of conservation of energy, this decrease in potential energy must be changed into another form. And in this case, it would be the kinetic energy. And once we calculate that, we can then find the velocity. So let me start. I'll call this position A, my starting position, and this position B just before it hits the surface of the Earth. That's A, and I suppose that I dropped this from rest. So in the beginning, it has no kinetic energy. I just dropped it. It's just potential energy, and it falls. So let me start. I'll start by finding the potential energy at A. Now to find the potential energy at A, I can use this formula. I would take minus G let me write down a number for G. That would be, okay, I'll write it down here. G would be 6.67 times 10 to the minus 11 in SI units. So I know G, and I know M, mass of the Earth. I need the mass of the Earth to do this. Let's see. Okay, let's say I have the mass of the Earth, and that's given by 5.97 times 10 to the 24 kilogram. So I have that. So I have everything I need. Okay, so to calculate the potential at A, I'll use this formula. I start by substituting the value of big G. Okay, it's 5. It's big G, isn't it? So that's 6.67. 6.67 10 to the minus 11. So that's the big G. Okay. Next one, the big M. 5.97 10 to the 24. So 5.97 10 minus 24. So that's my mass of the Earth. And m, little m is the mass of the ball, which is 0.2 kilogram. 0.2 kilogram over the distance r. That's the distance r, which is 100,000 kilometers. So 100,000. Now I need to have this in SI units, meaning in meters. So I need to add another 3 zeros to change kilometers to meters. So therefore, I now have all the numbers in, and I should be able to use my calculator to find an answer. And since it's potential energy, the units is in joule. Okay, so I shan't go through the calculation. I'll go on to show how we can do it in the next step. Now in the next step, I need to find the potential energy at B. Potential energy at B, I can now calculate using the same idea, except that the only difference is that at B, the R would be different. Okay, so I have the same numbers on top here. Okay, I'll just write it out. Okay, so 6.67 times 10 to the minus 11, and then 6.97 times 10 to the minus 24, and then 0.2. Okay, divided by, now this time I need to use at B is just before it hits, so the surface of the Earth from its center is 6380 kilometers. So 6380, convert to meters, another 30. So that gives us the potential energy at B, again in joules. So and there's a minus sign there, of course. So with these two numbers, I can now subtract them. I can now subtract them to find the difference. Now it would be a decrease in potential energy because this number would be bigger. If you look at those two, alright, they are the same except that the denominator here is bigger than here. Because this denominator is smaller than this numerical answer would be bigger. But because of the minus sign, it means that it's more negative. Okay, so the potential energy at B is actually less than the potential energy at A. Right, so let me take note of this result. So PE at B is actually less than the PE at A. Now to find the decrease in potential energy, so potential energy here is less than potential energy at A. So the decrease in potential energy, is equal to, right, the P at A, potential energy at A, minus the potential energy at B. So with those two answers, I can just put them in here and find a value. So this decrease in potential energy must be, it will be in joules. So that's the decrease. And then we say, because of energy conservation, this potential energy that has decreased is not just disappeared or been destroyed, it is converted into kinetic energy in this case, because we know that that this ball goes faster and faster. So therefore, this is also equal to the kinetic energy. So this is equal to the kinetic energy. So we have a number here that we can calculate from the above answers, and we know that the kinetic energy, is half mv squared. Right. So because we know the mass of the ball, we can therefore finally calculate the velocity. So if I call this answer E, then I can just rearrange this to give to find V by moving the 2 over to the other side, multiply by the E there, divide by the M here, move over to the other side, and then taking the square root. So whatever answer I have found here, I just substitute it into here. The mass would be 0.2, and with our calculator we can finally get the velocity in meters